Hello, everyone. Welcome to the MLOps 2021 conference. My name is Nadia, and I work at NILAS as a senior machine learning engineer. Today, I'm honored to be here and to have the opportunity to introduce one of our amazing speakers. Before starting, I would like to remind you that if you have a question, please post it in the chat. I will collect all the questions and ask them directly to our speaker after the presentation. So let's start. Our speaker is Rob High. Rob High is a Vice President and Chief Technology Officer of the IBM Edge Computing portfolio. High has architecture and technical strategy responsibility for offering that will enable a new generation of edge computing, where work is placed close to where data is produced and actions are performed. Prior to this assignment, he was the CTO for IBM Watson, responsible for setting the technical strategy and vision for IBM leadership in AI computing. High is recognized as a global technical leader, author, and evangelist, and was named an IBM Fellow in 2008 for his pioneer work in the field of SOA and for his leadership on WebSphere. Please join me in welcoming Rob High.
Excellent, Nadia. Thank you so much for the introduction. That was very kind of you. Good. Well, as Nadia said, I am the CTO for our IBM Edge Computing business. And what I want to do today is kind of focus in on how machine learning at the edge is evolving. And we'll spend a little bit of time talking about some of the market trends, but then I'll lead more deeply into how we're facilitating bringing ML and other artificial intelligence, or as I like to say, augmented intelligence capabilities to the edge. So let me just begin with a few of our core beliefs as a company, as a mission. These are things that clients have told us. These are things that we believe to be true about the world that we're operating. And it begins with that people really want to be able to make better and faster decisions. Latency in the decision-making processes has an impact on productivity. Quality has an impact on productivity. And at the end of the day, net returns on the investments that we make in our businesses. We also think that there's a rising cost to the amount of data that's being generated and transmitted, and especially in the context of a model where a lot of that data today is now being centralized, being transmitted to a central location, like a cloud, public cloud location, or even an IT data center location, and processed there. And the transmission costs are not just simply the cost of the network, but also the cost of ingress into those cloud environments, the cost of storing the data, the cost of just simply handling the data, even if it's not being processed. And what we've noticed is that more and more often, only a very small fraction of all the data that gets generated and sent to the cloud ever ends up actually being processed, which means that a lot of those costs are really kind of wasted costs or unnecessary costs. We also think that, of course, people are trying to protect their personal and private information. They're increasingly sensitive to their own personal information being given out and being exposed. Just as importantly, institutions need to be able to protect their private data, the data that really represents the status of their business, or anything that might be used by competitors to undermine the capabilities of that business or their current status and market position. And then finally, we're all concerned about how do we maintain resiliency? How do we continue to operate our business even when resources are down? Things like networks are unavailable to us, or access to cloud resources are down, or other things that can happen along the way that would disrupt our business. And so for all of these four things, we think that edge computing is an important ingredient in how we respond to those needs. For those who don't know, edge computing is largely the idea of moving workloads closer to where the data is created and where decisions are made. Where is that? Well, that's in where our businesses tend to conduct the majority of their business. If you're in manufacturing, that's the manufacturing floor. If you're in retail, that's the retail store. If you're in distribution, it's the distribution centers and the warehouses or the logistics facilities and vehicles that you have. In the future, as we get into more intelligent vehicles and intelligent roadsides, we're going to see those be the places where data is created and where the actions are taken. That is where we exist, where we operate as humans, and the decisions that we make along the way. So edge computing is emerging, and it's an important way of bringing that workload closer to reduce the latency, to actually reduce the physical distance between the creation of data, its processing, and the results that then inform decisions that we need to take. It is about reducing the bandwidth or the amount of network transmission that has to be performed when we collect the data and process it. It's about protecting the personal and private information that may be captured in that data so that it doesn't get exposed to others that might exploit it for nefarious reasons. And it's about being able to continue to operate your business, even if the network to your cloud is down or the network to your data center is down, and so forth. So that's what edge computing is. And edge computing really represents sort of the latest iteration in this pendulum that we as an industry seem to take every few years that shifts from centralized computing to distributed computing. We saw the era of mainframe computing. We saw the era of client server, which largely failed because, well, the task of managing getting the workloads into the client were too arduous. We've seen the internet re-centralize a lot of that computing and then redistribute that with mobile computing and then re-centralize again with public clouds. So now we're in the latest phase of this generational pendulum swing between centralized and decentralized. But what's interesting to note is that every time we go through this iteration, two things happen. One is we learn from the past. Each iteration, we learn the mistakes that were made before. As I said, in client server, the biggest issue we had there was how do you manage getting the client in place when you've got hundreds or thousands of these that you have to manage, and where the infrastructure is not all that strong for supporting that. The issue with mobile computing, well, although frankly we're still using mobile computing, but nonetheless, it's constrained by the fact that this assumes that every individual will make their own choices about what applications they host on their mobile device. And so all of that has risen to the point where now we can take advantage of those lessons learned and begin to solve those even as we enter into these next stages. The second thing that we learn as we go through these iterations is that the order of magnitude of number of things involved in these environments increases exponentially for every iteration. If in the client server era, we were dealing with perhaps hundreds or thousands of clients, in the mobile computing era, we're dealing with literally billions. In the edge computing era, we're going to be dealing with tens or hundreds of billions, or even more perhaps, numbers of devices that we are trying to enable to be part of this world. When we think about edge computing, we typically think about three distinct tiers. There is what we call the network or metro edge. This is largely the consequence of the work that the telcos are going through as they begin to transition to both 5G, but more importantly, to take advantage of all the available properties that they have, the locations they have that are now largely unoccupied to host enterprise computing. And of course, because they're often located in metro centers, they by definition tend to have a shorter distance to the clients that may need to make use of that enterprise compute capability. But the other two tiers of edge computing are tiers that exist on the remote on-premise locations where we tend to conduct our business, in the factory floor, in the retail store, in the distribution center or the warehouse, in the intelligent roadside, or even in our vehicles. And those we divide into two distinct tiers. There's what we call edge clusters or gateways, or sometimes the telco industry likes to call these MECs, multi-access edge computing capabilities, which are largely around IT equipment. And so it's a half rack, it's a industrial PC, it's a specialized appliance that's designed with IT principles in mind to host IT-based enterprise applications. But the other tier that I think is really interesting are the emerging number of what we call edge devices. An edge device is a purpose-built piece of equipment. It could be a camera, it could be a robot, it could be a vehicle, it could be an ATM or a kiosk, it could be a point of sale terminal. It's any of these things that are built for a given purpose, but that have compute built into them. So it's very unusual anymore to find a point of sale terminal that does not have, a processing unit in the point of sale terminal. Even cameras today, the video cameras that we use, the webcams, as we like to call them, that we attach to our computers, more and more often, those cameras have compute in them. And more often, that compute is actually quite sufficient to do some very interesting analytic right there on the camera. And of course, most industrial robots these days are built with compute. Of course, each of these have a different amount of capacity. Typically, an edge device might only have one or two chips, maybe a couple of cores, maybe a quarter gig or more of memory. Relatively small, large enough to do some very interesting things, but nonetheless relatively modest in terms of size. Edge clusters tend to be also resource constrained. They're bigger than an edge device, but nonetheless have limitations. And of course, metro and network edges have more capacity to do even bigger workloads. But all of these tend to be much smaller than what we would typically find in a private IT data center or a public cloud. What is interesting, however, is that all of these, no matter how big or how small, are now capable of running containerized workloads. And this is important because what it allows is that for us to start thinking about all the work that has gone on to create cloud native workloads in the cloud, that is containerization, componentization, separation of concerns, CI/CD, DevOps, agile development, all the things that we associate with cloud native development practices, which have really become the gold standard for software engineering, now can be brought to these edge locations. We can run Kubernetes container runtimes on network or metro edges or in edge clusters. We can run a Docker runtime on a Linux distribution on an edge device, even a very small device that we wouldn't normally think of as being sort of a compute. Like I said, perhaps it's a web camera, but nonetheless, a lot of these cases, these web cameras are built running Linux and on which we can run Docker runtimes. And so that kind of unlocks the idea of a multi-tier distributed computing application where we can place the right workload at the right place at the right time based on the capacity and capabilities, and more so the intent that we associate with each of these. And of course, the workload that we talk about most often here is machine learning based workloads. Now, it's not limited to that. Obviously, we can do other procedural things, but the things that are most interesting and exciting are those that do things like visual recognition or acoustic recognition or speech recognition, or just even basic ML-based analytics for doing time series analysis, et cetera. And these are all the kinds of workloads that we can place in these edge locations to bring advantage for the lower latencies that edge computing provides, or the higher bandwidth that it provides as you localize that work. And all of that is what we call the edge. And of course, that's not to invalidate the relevance of more traditional IoT sensors. Those still exist. And those are still my main source of the data coming into these systems. But that now has become a front end to more robust compute that is now available locally within those environments. I should also highlight here the role of 5G and how 5G is accelerating adoption of edge computing. But 5G is both public 5G and private 5G. And private 5G is really quite interesting when you think about the role of these systems. Now, it's also important to understand how fast the transition is occurring. As of 2019, 2020, about 10% of all enterprise workloads were at the edge. Most of the workloads that are performed are either performed in IT data centers or in public cloud locations. But Gartner estimates that by as early as next year, we're going to see a massive shift in the amount of processing being performed at the edge. And that by the end of next year or early into 2023, we're going to see as much as half of all the enterprise data that's created at the edge being processed there at the edge as well. And then as we move into 2025, that jumps to 75%. So you can see this massive growth in the amount of compute that's being applied to addressing and understanding and providing inferences from the data that we're generating and moving that workload out to the edge. Now, that's not to say that cloud computing goes away. This is by no means arguing that cloud investments today are no longer valid, but rather that edge computing is going to grow at a faster rate. And in fact, in many cases, the edge computing will drive more workloads back to the cloud. It's sort of an interesting effect that occurs when we have these distributed systems. But as I said, each of these tiers represents a different amount of capacity, and they largely represent a point of trade-off between the amount of capacity that you have in each of these tiers, which is really kind of represented as cost, versus the latency that you get from that, which is measured primarily in terms of benefit. And so if you put a piece of workload on an edge device, you will typically enjoy less than 1 millisecond latencies for that. But you pay a cost for that because you're paying a premium for that because the resource is constrained. Whereas if you move workloads into the edge cluster space, you're going to typically see 5 to 10 millisecond latencies. You're going to have a little bit more capacity, and so therefore your cost of compute is going to come down. But then if you move into the network edge, you're going to have a lot more capacity, therefore a lot less cost, but your latencies are going to grow and probably to the 10 to 50 millisecond latency range. Of course, all three of those are going to be more expensive than running things in a cloud, but also a fraction of the latency you would typically find if you place things up there. So when you think about your workloads and think about how latency sensitive it is, you begin to build a picture for deciding where's the right place for that workload to reside. Where should I be placing that workload? Should I put it in the cloud? Should I put it in the network? Should I put it out at the remote on-premise locations, what we sometimes refer to as the far edge? Should it be right there on the device itself? And those are choices that are now becoming available so that we can now represent a continuum of trade-offs over those placement decisions. If you're surprised by this idea, you should just take a quick look around the marketplace. We estimate there's probably as many as 15 billion edge devices already in market today. 15 billion. And we think that probably jumps to around 150 billion over the next few years. And you can see this if you just kind of look and do a quick survey. This is just a small sampling of all the quote edge devices and edge equipment that's now available in market that's being used in production environments. Whether those are specialized devices like the Eurotech Boltgate or the HP retail solutions, whether they're more general solutions like the ATOS Boltsequena or Dell Power Systems or the Intel NUCs, or highly purpose-built equipment like industrial robots and intelligent power control systems, or some of the ATMs that we see, which have already been built with compute in them anyway for a long time. And then virtually every automobile manufacturer that we've talked to is at some stage of re-architecting their vehicle to consolidate all the available compute on those vehicles into a general compute complex, which really unlocks the potential for bringing a lot more compute capabilities into the vehicle and to unlock sort of the innovations that can be brought into the vehicle experience, whether that is really exotic things like fully autonomous driving or even partial autonomous driving, or driver safety capabilities, usability features, driver assistance or passenger assistance, all these kinds of things that are now made possible as these architectures come online. IBM has a very rich portfolio. I'm not going to go into these details right now, but we basically address capabilities at every tier across the distributed computing space, all the way down to very small edge devices, but with a tie back to the work that we've been doing in hybrid cloud computing. The thing that's motivating edge computing from a business standpoint is really digital transformation. The idea that you can create new experiences to fulfill sort of that gap that occurs sometimes when you now no longer have a human to interact with and you're interacting on your phone with a digital presence. The more that mobile device or edge device is able to gather about the environment that you're operating in and create context for the interactions that you're performing, the better job it can do at anticipating what you really mean, interpreting what you really want, to be able to anticipate how to serve you better. So context matters, as we know, within AI systems. And the more data we can collect around in the environment that you exist as a end user, the better the digital representation can be at serving your needs. And of course, 5G, as I mentioned before, is a huge catalyst here. First of all, of course, 5G is unlocking a tremendous amount of capital investment. And that's investment that's not just going into the creation of the 5G infrastructure, but also how the peripheral devices that are connected to the 5G will take advantage of lower latency and higher bandwidth that 5G offers. And in doing so, is also driving a lot of innovation around those use cases that will leverage 5G. Now, that's not to say that edge computing is dependent on 5G. We can do edge computing with 4G or LTE or even 3G or even landline connected devices as well, for that matter. But 5G certainly accelerates its use and the investment in innovation that's going to unlock value between edge devices and 5G. You could also argue that 5G is somewhat dependent upon edge computing because in order to really fulfill the promises of lower latency and higher bandwidth, you can only do that by overcoming the laws of physics, which essentially requires that we move the workload closer or to reduce the distances between the device and where the work is being performed. Now, just a quick survey of the market. About 27% of enterprise customers that we have surveyed are already making use of edge computing, or at least aligning their businesses to get advantage from edge computing. In the next 3 years, that's going to grow to half. Half of all enterprise businesses will find ways of exploiting and leveraging edge computing. And this coincides with the point I made earlier about the growth of edge computing and how massively that's now emerging into the marketplace. The most frequently cited use cases have to do with process optimization or situational awareness or human-machine collaboration or decision support or risk assessment. And it's interesting to note that in almost all of these use cases, there is opportunity and really almost a dependency on making use of machine learning as the underpinnings for which the analytic is being performed in these processes depends. So ML is absolutely essential. As I said before, ML or AI is probably the most commonly referred to workloads when people talk about edge computing. And they're most frequently being used in things like industrial and manufacturing, in infrastructure. And by this, what I mean is buildings and facilities. I'm not talking about IT infrastructure here, although that too also has some utility in edge computing. Retail, of course, is a very commonly cited use case scenario for edge computing, and services. And by that I mean the kinds of services industries, including financial services, insurance services, and of course other forms of services. One example workload that I like to highlight is one that we've been doing around production quality, and that is recognizing or monitoring the quality of the work going into welding. If you're familiar with the welding processes in manufacturing today, typically to tell whether or not you did a good job welding or not, or whether a robot did a good job of welding, you have to kind of do a destructive test. You have to, cut open the weld and look at it, or take it off the line and do an X-ray. And so it's a laborious and tedious task to really determine whether the weld was performed properly or not. Well, we can use video analytics to recognize using the infrared spectrum whether through the heat signature of the weld is good or bad. And so this allows us to monitor the quality of the weld in real time, and allows us to, of course, do that without being destructive to the work that was being done by the weld. And of course, that represents a tremendous savings in terms of the cost and remediation of that environment. So this is a really good example of where AI being applied at the edge makes a lot of sense, because if you think about the amount of data that has to be collected from that video camera in order to do that analytic, it would be overwhelming if we had to send all that data back to the cloud. We have found utility in edge computing in virtually every industry. And I'm just going to give you a couple of examples here. In transportation, everything from monitoring the performance of equipment to being able to optimize transportation routes. There's a piece of work that we just completed. Actually, it's in flight right now with the Mayflower autonomous ship, where they're using AI on board with edge computing to help the ship navigate autonomously from Plymouth, England to Plymouth, US, Plymouth, Massachusetts. That's underway today. In fact, you can go to the MAS400, MAS400.com site and actually watch its progress and learn more about the technologies that are there. But again, a good example of edge computing in transportation. Vehicles, as I've already mentioned, are already going through a fairly massive transformation and enabling architectures to allow for much more container-based compute from machine learning on those vehicles. Of course, kiosks, healthcare, manufacturing, I've already mentioned. Distribution, agriculture, piece of work that we're doing with a institution in Europe that is using AI in the field to recognize crop yield and to inventory crop availability in case of national emergency. The other thing they have to recognize is the production of data. And as we all know, especially any of us who've been involved with AI, machine learning, the amount of data that is being generated and the rate of growth is just phenomenal. It's just outrageously large. And of course, again, you got to think about what is the cost and complexity of moving that data around in order to get any utility out of it. And instead, what we prefer to do is use edge computing to lower the latency, therefore deal with the ephemeral issues of data, collect more contextual information that makes analyzing the data easier and better, and then removing some of the messiness that typically is associated with unstructured information. So for all those reasons, we're seeing a lot of interest in using ML at the edge. The other thing that's worth just noting is sort of the transformations occurring in the OT industry. Of course, there's been this tension between OT and IT for really decades, and that's not going to go away. OT is certainly not going to go away. I think there's always going to be a little bit of a debate as to whether to do things with OT versus IT. But as OT vendors respond to the demand for more and more analytics within their OT systems, what they're discovering is that they can only get that analytic in there if they're able to hire data scientists who know how to build those analytic algorithms. And data scientists, of course, are born and grew up on IT technologies for doing the analytics, whether that's with Keras or TensorFlow or PyTorch or any of the sort of traditional and commonly used tools and libraries and kernels that are now associated with machine learning. Almost all of those were born in the IT world. So in even those cases where you've got OT vendors delivering OT, embedded in there oftentimes is IT under the covers. And of course, the growth is tremendous. And one of the things I do want to mention here is the effect that COVID has had on the growth of digital transformation. Remember, I talked about that earlier, and the importance of digital transformation to motivating the need for edge computing. Well, COVID has accelerated digital transformation. If you think about it, you can't really go into any restaurant today without getting a touchless menu. That is a QR code, so you can pull up the menu on your phone. Of course, in many cases, retailers have had to convert to some form of buy online and pick up at the store to avoid requiring their clients come into their stores. And of course, we've seen a tremendous shift in the way that work-related, employee resources are deployed into our offices. And so all of those things are going to drive more demand for both digital transformation, but also specifically the need for edge computing. We should also be conscious that edge computing is not the same as cloud computing. They are similar, of course, but the differences are that everything that we do in the cloud tends to be very homogeneous. We have lots and lots of servers, but they all tend to look the same. When we get out to the edge, we're dealing with different devices and different architectures and different configurations and different purpose that is arrayed across literally thousands of different edge devices and servers and clusters. And so that diversity is a pretty substantial form of complexity that you have to deal with. And in addition to that, of course, we also have to deal with the dynamism. This world kind of moves around a lot, both physically, but even more so in terms of the things that we're doing with that equipment out there on the production floor or in the retail store and so forth. Much more dynamism of the physical world in the edge computing space than we see in the cloud computing space. And finally, of course, we've got security issues. This stuff is out in the wild, right? There's attack surfaces that we have to worry about that we didn't have to normally worry about in cloud computing. And then when you take all those things, diversity, dynamism, and security, and amplify that by literally thousands or tens of thousands or perhaps even millions of edge devices, what you end up with is a pretty substantial administrative problem. And so that's one of the things that we've been working on within IBM is creating a product that's capable of enabling you to manage getting the right workload to the right place at the right time and keeping it up to date in the presence of diversity, dynamism, to do so securely, and to be able to do that at massive scale. Today, within this product, we can support up to 40,000 edge devices from a single administrator responsible for getting all the containers that make up your systems out there deployed to your edge environment. This product is built on open source. It's part of the Open Horizon project that has been donated to the Linux Foundation and is being standardized there. Open Horizon now has graduated to stage 2 as a standard and is really building a very strong community that we think we can use to help facilitate accelerating adoption of edge computing, but more importantly, enabling enterprises to really do a good job of managing their edge environments. So I've included in the materials that we're going to hand out to you here today a list of links to other information that covers topics that I didn't get a chance to really talk about here today. But I want to stop there and kind of open it up to questions if we have time.
Hi, Rob. Yes, we do have time, and I see a couple of questions in the chat. The first question is edge computing here just federated learning?
Federated learning is not the same as edge computing, but federated learning is an important use case that I think is surfacing in edge computing. If you think about the topology of edge computing, let's say you're a retailer and you've got compute in every one of your stores, and each store, of course, is exposed to a different set of information, a different set of circumstances, different clients, different behaviors, different even inventory perhaps. You know, some of those may be regional differences, some of those may be demographic differences, some of those may be simply preferences that are different from one location to the next. And you're trying to build, let's say, an algorithm that will predict the kinds of offers to make to your clients at checkout. Well, you'd like to be able to do that based on some aggregate global view of all the things that your clients do and what they do next, and apply that to each store, given that only every store only has a very small subset of the data that you're trying to understand, then it becomes an ideal situation to do federated learning, to do learning locally based on that local data, and then to synthesize a global model out of all those micro models that were created at the store. So federated learning has a lot of applicability to edge computing, but it's not synonymous with edge computing.
Thank you so much for the clarification, Rob. I'll go with the second question. Is there a segmented approach that you could suggest to dividing the workload between edge devices, network edge, and cloud, considering time latencies vis-a-vis and workload nature of processing required? For example, single data, sorry, go ahead, I'll finish later.
Yeah, so there's no set formula for this. This is very situationally dependent, and you have to kind of understand your use case. But the generalizations I can make about the choice about where you're going to place workloads have a lot to do with the importance of latency to the end effect. There's probably not that many automated processes that need sub-millisecond latency to be able to choose what they're going to do physically. So if you're on the production line and you've got 100 parts per minute that you're feeding through your production process, and you're doing quality inspection on that, and you're trying to decide whether or not the part that just got manufactured is of good quality or bad quality, to decide which bin to put it in. Well, that probably doesn't need sub-millisecond, but maybe somewhere between 10 and 50 millisecond latencies are sufficient, which would imply that you don't need to have that algorithm running right there on the machine. If, on the other hand, your algorithm is designed to protect workers from getting too close to the production process, to recognize and sense that somebody just put their hand too close to, a chopping machine or some other mechanism that could be quite dangerous for them, you don't want any latency in that decision at all. You want to be able to shut that machine down as quickly as possible. And so therefore, sub-millisecond latencies are probably very important to you. Now, of course, again, you're going to pay a premium for that lower latency. So you want to kind of measure the value that latency brings for you against the cost of the premium resources that you're exploiting to put it there. And then, of course, I always talk about this in terms of latency because that's easy to understand, but also think about it in terms of bandwidth and the amount of data that you're generating and having to traffic between locations, because that's another expense that you want to be able to measure against in these cases.
Thank you so much. The examples were amazing, really clear to understand the difference. We have, I think, yes, other two questions. So how can we incorporate monitoring into the edge computing offering you currently described?
Yeah, so IBM Edge Application Manager, it does its own internal monitoring for changes that would affect the decisions about where things are placed. So that's kind of built in, but there's a lot of cases where people want to add additional monitoring capabilities around, say, the environment that is, that the machine is deployed into. And it's not atypical for people to write their own containers that collect up additional data from sensors that are monitoring the environment that you're in, or maybe internal sensors, including CPU utilization and GPU utilization and temperature fluctuations, et cetera, and then to pipe that back to a central location to be presented through something like Grafana or something like that. And of course, since what we're doing within IAM is deploying containers, if you write that kind of monitoring algorithm as a container, then of course we can deploy that to the edge as well, to connect it to the sensors that are available there to pull back that data back to some central location.
Awesome, thank you so much. We now have a question more product facing. So does IBM IoT has connector to different IoT devices?
So there are a number of connectors that are available. It's always a little bit difficult for me to say or answer this question precisely because, first of all, there's a huge range of devices out there, and there's the good thing about standards is there's so many of them. There's lots and lots of standards for how these IoT devices get connected. So yes, there is a large range of IoT connectors available from the IBM product. Of course, there's also additional connectors available in the open marketplace too. There's a number of our own partners who provide these kinds of connectors, and people, including people like Foghorn and Clearblade, who supply their own sets of IoT connectors that could be used in these environments. And of course, there's also open source. Fledge, as an example, in the Linux Foundation, is an open source project who also includes a number of IoT connectors.
Awesome, thank you so much. We do have the final question. So people, if you want to ask any other question, that's the right moment. Otherwise, after this answer, we are gonna close this pretty good presentation. So, I see another coming. What data model standards are emerging to enable edge device manufacturer and implementer to more seamlessly integrate multiple devices as data source?
Yeah, so I have to admit, I'm not that familiar with the manufacturing standards, so I can't speak to that very well. But I can say, though, that at least in the automotive space, there are the ADAS standards that are coming out, which largely dictate how things are implemented and managed in vehicles. The OT vendors both contribute and are part of standards organizations that are defining this beyond simply SCADA. And even though I can't cite what those are because I'm not that familiar with them, I am aware of the fact that they're working on those.
Thank you so much. So we do have the last one. Do you see all ML workload eventually being done in the edge in the future? Or do you find the split between edge and cloud the end game for machine learning?
So, like I said, AI and machine learning are probably the most commonly cited workloads that people talk about when they talk about the edge. But no, I don't think that all machine learning will be performed at the edge. And of course, just kind of decompose that further. If we're talking about training, there's still a fairly substantial expense associated with training a machine learning model. And when you're dealing with large data sets and many epochs and layers in your machine learning model, it's almost certain that you're going to want something of substantial size and power, the kinds of things we typically find in the cloud to do that machine learning training with. As I mentioned earlier, federated training is also an interesting topic, and that has the benefit that because what we're dealing with is smaller data sets and less complex problems, generally what we do, the compute power that we have at the edge is sufficient. But of course, even then, we presume that there's going to be small micro training activities occurring at the edge and then aggregated at some central location that creates a synthetic model that is more global in nature. On the inferencing side, I definitely see a lot of migration of machine learning based inferencing going on at the edge. Like I said, that's sort of the thing that people cite most often. But you got to look at the nature of what you're trying to do. If what you're trying to do is detect a quality problem, you're going to want to run that in an environment where you get lower latency and less bandwidth constraint. But if you're trying to do is trained analysis across a regional portion of your business, then no, you're going to want to aggregate that and probably put that in a more central location.
Okay, thank you so much. This was very clear. Okay, so we practically don't have any other question, but we are just in time. So I'll say that perfect. And I see some thank you coming for you for your answers. So thank you so much, Rob. Thank you so much for being here at TMLS, for sharing with us this very informative presentation and for answering all the questions.
Absolutely. Well, thank you, Nadia. And great to see you, Ali. We'll talk to you later.
Bye, everyone.